Good morning, and today we're looking at 2018 AP Chemistry's FRQ question number 5. Question 5 starts with this equation. HF plus H2O liquid gives us F minus aqueous and H3O plus aqueous. And it says the ionization of hydrofluoric acid in water is represented by the above equation. If in a 0.0350 molar hydrofluoric acid solution, the percent ionization of HF is 13%. Question A, two particular representations of the ionization of hydrofluoric acid molecules in the 0.0350 molar HF solution are shown in Figure 1 and Figure 2 below. Water molecules are not shown. Explain why the representation of the hydrofluoric acid molecules in Figure 1 is more accurate than the representation in Figure 2. The key below identifies the particles in the representations. So right off the bat, it tells you the answer. It tells you that 1 is a better representation than 2. What we have to figure out is why. So let's take a look at these two molecule structures. If we look at Figure 1, we've got HF here, and we have a single F minus and a single H3O plus. If we look over here, we have a bunch of F minuses, a bunch of H3Os, and no HF. So why is Figure 1 better than Figure 2? There are two ways to think about this. The first is if we talk about the percent ionization. It says 13% is ionized. Here, we have no HF. That means this is 100% ionization. There is no HF left over, which means that this is a bad representation because we know it's only 13%. This one has both HF and F minus and H3O, and the H3O and F minus are very small quantities, very small concentrations. That tells us that way. Alternatively, we can go, well, HF is a weak acid. How do we know it's a weak acid? Well, it's not one of the 7 strong ones we've had to memorize. Since it's a weak acid, it won't dissociate completely. This one depicts a complete and total dissociation with no HF. This one over here shows incomplete dissociation with some of the HF dissociated, but most of the HF still in HF combined form. Either way works. But you do need to cite that either the percent ionization is 13% or that HF is a weak acid. Either way works, but that is how you do A. On to B and C. Parts B and C get a little more math heavy of question 5. Let's start with B. It says use the percent ionization to calculate the value for Ka for HF. If we're talking about calculating Ka, we're going to be using an ice table. So what we need to do is we need to go up to our percent ionization, which is 13%, and go, okay, how can we use that? Well, the HF is going to split up into F minus or H plus, which will then attach to the H2O to make H3O. But long and short, this is going to go down, these are going to go up. How much, however, is this going to go down by? Well, 13% of it is going to ionize, which means 0.0350 times 0.13 equals 0.00455. This number right here is your change. It's how much this is going to go down by, and these two numbers are going to go up by. So minus 0.00455 plus 0.00455 plus 0.00455, which means ultimately these are going to be 0.00455, 0.00455, and this one would be then 0.0304. Once you have those values, finding your Ka is just as simple as products over reactants, remembering that the H2O doesn't factor because it's a liquid, and liquids have a concentration of 1. So your Ka will equal F minus's concentration over times H3O plus's concentration over the HF concentration, which if we plug in all of our numbers, the 0.00455, 0.00455, 0.0304, we get a value of 6.81 times 10 to the negative fourth. And again, 3 decimals because we have 1, 2, 3 sig figs there, and we have 1, 2, 3 sig figs here. Part C says if 50 milliliters of distilled water is added to 50 milliliters of 0.035 molar HF, will the percent ionization of the HF in the solution increase, decrease, or remain the same? Justify your answer with an explanation or calculation. And the first response most people have is, oh, it's a Le Chatelier problem. We're adding water. It'll shift it towards the products, which will increase our ionization. I'm done. But we can't do that. The issue here is that H2O doesn't show up in your Ka expression. It won't shift your equilibrium because it's not a factor. We can't use Le Chatelier, and that's what they're trying to do here. They're trying to trip you up and be like, do you know when you can use Le Chatelier? Yes or no? So don't fall for the trap. What we have to do instead is we have to go, okay, we have a Ka expression, right? And our Ka is going to equal F minus H3O plus over HF. Doubling the amount of water. We're adding 50 milliliters to 50 milliliters, doubles our water, which will have our concentrations. So, with the water added, with the add, we're going to have half as much F minus, half as much H3O plus, and half as much HF. Okay? Which, if we pull out all the halves to the front, we'll get half times half divided by half. Times this F minus H3O plus HF, which is the same as Ka. I'm just going to put this in brown to make my point. Okay. Half over half cancels, which leaves us with half. Our Ka value. Now, this would be a Q value, because it is not actually Ka. So Q equals half times Ka. Now, since Q is less than Ka, we need to shift towards the products to reestablish equilibrium, which means in this case, yes, the reaction would shift towards the products and increase the percent ionization. Now notice how this is similar to Le Chatelier, but we can't take that answer for granted because Le Chatelier doesn't predict the species of concentrations 1. Adding more solid or adding more liquid to a concentration is not covered under Le Chatelier, strictly speaking. So do not fall into the trap of assuming that this is a Le Chatelier problem because, once again, we're adding a liquid, not innocuous. Thank you. Have a good day.